So to recap, sum of an infinite series, one that goes on forever, right? So finite series ends, infinite series doesn't. Here's a finite arithmetic series, right, where T1 is 1 and D is 1, and we get 1 plus 2 plus 3 plus 4, which is 10. Here's a geometric series, T1 is 1, R is 2, and we've got 5 terms in that series, and it adds up to 31. Okay, moving on. Moving along. Can you determine the sum of an infinite series? So if it never ends, can we actually add it up? So what would happen with 3 plus 7 plus 11 plus 15 and so on? What would that, is there a sum if we keep adding? No, right? Because every time you add on, you're adding on a larger number. So there is no sum for this, right? There's no sum. That won't add up. How about 3 plus 3.1 plus 3.2 plus 3.3 and so on? Will that add up, or will there be a number it's equal to?
Do you want to write all this down?
Yep.
Can you slow down a little bit?
Yeah, I'm giving you time. You have time on the first page.
I'm going to slow right here.
Will that add up? That's okay. We can discuss while you write. No, right? It's just gonna. It's also gonna get bigger and bigger, right? We can't really, you know. So no. That should be a 2. 3 plus 2 plus 1 plus 0 minus 1 minus 2. If we keep going, will that add up? No. So I think there's a problem. Like an infinite arithmetic series, because you're always adding the same number on each time, they're always going to get pretty big, right? They won't end. Okay, let's take a look at, how about this geometric? 3 plus 6 plus 12 plus 24 plus 48. What happens to each term? Gets bigger and bigger and bigger, right? So that won't add up. You know, no sum. Okay, what if we flip signs? So we go 3 minus 6 plus 12 minus 24 plus 48. Will that add up? No, we don't know, right? Like, we know that it's going to get large positive and large negative, and it'll keep flipping signs. 3 plus 3 plus 3 plus 3 plus 3 ad infinitum. No, right? It's just going to get bigger and bigger and bigger, right? There's 1,000 3's. 3 minus 3 plus 3 minus 3 plus 3 minus 3 plus 3 minus 3. If it's finite, it has a sum, right? I mean, it's either 0 or 3, right? It goes 3, then the next sum is 0, the next one is 3, then 0. And then, but if it's infinite, then, yeah, we don't know. Why? Because it doesn't end, so no sum. How about a half plus a quarter plus an eighth plus a 16th? So if the numbers you're adding get smaller and smaller and smaller, will this have a sum? Don't know, but this might require some further investigation, right?
Wait.
What we're going to look at is, for this infinite geometric series, right, we can determine its partial sums. In other words, we can work out S1, right? What's S1? 1/2, right, which is 0.5. What's S2? Come on, S2. You guys lost the ability to add fractions? S2. What's a half plus a quarter? 3 over 4. Or 0.75. What's S3? What's 3/4 plus 1/8? 7/8. Okay, 1/2 is 4/8, 1/4 is 2/8, 1/8 is 1/8. We have 0.875. What's S4? 15/16. You start to see a pattern, right? S1 is 1/2. S2 is, we're looking at the bottom number here. It's a half, then it's 3/4, 7/8, 15/16. So we start off a half, 3/4, 7/8, 15/16. What do you think the next one is?
1 over 2.
31/32. 31 over 32. What's after that?
63, 64.
Okay, so are we getting closer to any particular value?
Yeah.
What value?
1.
1. Getting close to 1.
But not gonna reach it.
But we're not going to reach it. But so this actually is Zeno's paradox. You ever hear of Zeno's paradox? So Zeno said, if I'm going to fire an arrow from the front of the room to the back of the room, it'll never get there. And the reason it won't get there is because in order to get there, the first thing it's got to do is go halfway there. Right? So I traveled half the distance from the front. That's a half. Then, in order to get the remaining distance, I have to travel half that distance, which is a quarter. In order to go the remaining distance, I have to go half of that, which is an eighth. In order to go the remaining distance, I have to go half of it. Well, I can always go half of the distance, right? So then he said, well, you're never going to get there. And somebody said, line up against the wall, I'll fire an arrow at you. And he said, no, wait, you know. So Zeno's paradox says you're not going to get there. Or, same thing, you could have a pizza. And you want to eat the pizza. Okay, so I'm going to eat half the pizza. Then I'll eat half of what's left. So I eat a quarter of it. Then I'll eat half of that, which is an eighth. And half of that, and so on. So you'll never really be able to eat the entire thing because you can always split it into half.
What's the point of that?
Part of that is it's a paradox because we know that you can eat the whole pizza. We know that the arrow will reach the far wall.
Yeah, but that's like a pointless paradox.
So that means that we can sum up an infinite geometric series.
What do you use it for? What's its like practical application?
Summing up an infinite geometric series. So if we want to sum this up, a half plus a quarter plus an eighth plus a 16th, we can use the table feature of our graphing calculator. Okay, actually let's get out the graphing calculator and we'll... So, hang on. Yeah, that's okay. What do I want? TI-83. TI-83. Oh, hang on. So we need, so we want a formula for S sub n, right? Okay, so S sub n is T1 times r to the n minus 1 over r minus 1, which is 1/2, that's our first term. 1/2 to the n, that's our common ratio is a half, minus 1. Ladies, thank you. Over a half minus 1. So S sub n, here's the formula, right? 1/2 to the n minus 1. That's what it simplifies to. So we can put that into our calculator, right? So y equals 1/2 to the n. So let's go bracket. One divided by 2 bracket to the power of x, and then subtract 1 minus 1. And if we go second function graph, that'll put us into the table. Oh, sorry, there's a negative in front, so hang on, let's adjust that. So negative, I need to insert a negative, second insert negative, and I'll need a leading bracket there, and I'll need a trailing bracket at the end. And bracket. Okay, second table. So a half, 0.75, 0.875, 0.9375, and if we keep going down, 0.999999, lots of nines, and then a 1. Okay, now, it's not actually a 1, but that's all that it can display. It's 0.9999998, so on, right? That's when we had 24 of them. 25, 26. Eventually, to the accuracy of the calculator, which is about like 14 or 15 decimals, like eventually it's just going to give you one. That's all that it can do. That's like 41, sum of 41 terms, right? So we can see that, yeah, we do reach a limit, and that limit is 1. Okay, we can see that the values of the partial sums get closer and closer to 1. We say that the sum of the series is 1. So we say a half plus a quarter plus an eighth plus a 16th, and if you go on forever, so if you sum an infinite series, this infinite series, you're going to get 1. All right, so now we know that, yeah, there are some infinite geometric series which have a sum. Okay, so I'll let you copy that down. Yeah, so let me do this and pause. Okay, so then at this point, if you're watching this because you weren't here, if at this point you can write this down, you can just pause, write this down. Here's the characteristic, right? An infinite geometric series will be convergent if the R value is between -1 and 1, not including the 1 or the -1, right? Basically, if it's a fraction. So a half, a quarter, 5/6, 7/8, not 9/8, that would be over 1, okay, or the negative value. This is the formula, okay, so let's plug in. So here we're just going to look, okay, what do we got? Well, we know that T1 is equal to a half, R is equal to a half. The sum of the infinite series is T1, 1/2, over 1 minus 1/2, which is a half over a half, which is 1. Okay, so that works, right? So you now have a formula where you can add up a convergent series, right? Convergent meaning it will come to a value, meaning the R value has to be between -1 and +1. That's what gives you a convergent series. Okay, questions? No? Moving on. In a sec. All right, pausing for a moment. No, it isn't. I'm just saying pause.
Pausing for a Bronado.
Okay, ready or not? Oh, wait, too far. Which infinite geometric series is convergent? Determine the sum of the series. So what we need to do is be able to look at a series, say if it's convergent. If it's arithmetic, it's divergent, right? There's no way, it just does not converge. If it's geometric, it's either arithmetic or. Okay, so T1 is 4, what's R? What's R?
4/3. No.
No.
1/3.
No.
3/6.
Yeah. Okay, R is 3/2. Divergent. Okay. So to be convergent, R has to be between -1 and 1. Basically, it's a fraction less than 1, right? Whether it's positive or negative. 12, 3, etc. So T1 is? R is? 1/4. So it's convergent. S sub n, or sorry, S infinity, so the sum of the infinite series is T1 over 1 minus R, which is 12 over 1 minus 1/4, which is 12 over 3/4, which is 12 times 4 over 3, which is 16. Okay, so this particular series will add to 16. Basically, this adds to 15, and then this part adds to 1. Just like the half, the quarter, the eighth adds to 1. So does 3/4 plus 3/16 plus 3/64, and so on. Okay, you don't need to worry about that though, right? Because the formula takes care of it for you. (36 minus 12). Okay, so T1 is 36. R is -1/3. It's convergent between -1 and +1?
We notice this.
Okay.
What? We notice this.
Oh, I don't know. Who knows? Gauss? I don't know. T1 over 1 minus R is T1 is 36 over 1 minus -1/3. Hang on, let me move this down. One minus -1/3, which is 36 over 4/3, which is 36 times 3/4, which is 27. Now the reason there is because our sums are always going to be positive here, right? 36 is the first sum, then 36 minus 12, so it goes from 36 to 24 to 28 to 28 minus to 26 and 2/3 to, right? So it's bouncing around the 27 mark, right? Just like the other one. The other one actually grows to 1. Right, a half plus a quarter plus an eighth gets bigger, bigger, bigger. If you graphed it, it would look like this. It would be starting like this and would rise and become 1. If you graph this one, it starts out here, then goes down here, up here, down here, but it zeroes in on, or it settles down on 27. Okay, that's the number it's going to get close to. Okay, unlike on the first page when we looked at where there was a minus in that, it wasn't getting close to a value. It was just getting bigger each time. Okay, need some time? For what values of x will the series 30 over x plus 20 over x squared plus 40 over 3x cubed plus ... be convergent? Okay, so convergent means it's got to add up, right? It's got to, so the r value, so okay, what's T1? What's T1? 30x, right? We don't actually need that for this, right? But I like listing T1. What's R?
2/3 x.
Yeah, so R is equal to, so let's, it's not immediately obvious, right? So R is 2x over 3, right? So if we multiply that, I'm going to get 40x cubed over 3. Yeah, that's what we get, right? Or 40/3 x cubed. You can leave the x to the side if you like, right? So we just think of this as 2/3 x. Okay, so what do we know? Well, we know that -1 is less than 2/3 x, which is less than 1, right? We know that R has to be between -1 and 1. So, how are we going to solve this? Why don't we do it in 2 pieces? Yeah, let's do it in 2 pieces. Let's say, okay, let's just do 2/3 x has to be less than 1. Okay, so let's solve that. What does that mean? You multiply both sides by 3 over 2, right? To get the x by itself. So x has to be less than 3/2. But there's another part to it, right? Which is also that -1 has to be less than 2/3 x. Okay, how do we solve that? Multiply both sides by 3 over 2. -3/2 is less than x. What's another way to say that? Yeah, well, okay. I meant, can we throw the x on the other side, or x is greater than -3/2? So x has to be less than 3/2, but greater than -3/2. So how do we write that? that x has to be between negative 3 halves and positive 3 halves.
That's it.
That's it.
That's a valid answer.
Yep.
Incorrect.
That's your answer. Those are the values of x for which this series will be convergent, right? Because it'll lead to an r value between negative 1 and 1. Okay. Now, I wouldn't really want x to be 0 because we just gave you 0, 0, 0, 0, 0, 0, you know, which, okay, well. So that's kind of a trick, but it would work, right? It would still be a convergent series. It would just be 0. But you know, you could try this out. You could say, well, so okay, what if x were 1? Like 1 fits that, right? Because then we get 30, 20, 40 over 3, etc., right? And the r value here is 2/3, which is between 1 and negative 1. Okay? You put a 3 halves. Well, really, here's your r value, right? So if you put 3 halves in for x, you're going to get 3 halves times 2/3, which is 1, right? But we can't be 3 halves. We have to be less than 3 halves. So we could just go closer to 3 halves, put that number in. This would be a number less than 1, right? Okay? The sum of an infinite geometric series is 20. If the first term of the series is 16, determine the value of the common ratio. Okay, the formula for the sum of an infinite geometric series involves 3 quantities, right? The sum at infinity, t1, and r. If we know 2 of those 3, which we do, okay, so formula is sum for infinity is t1 over 1 minus r. Okay, the sum is 20. That's 16, and r is r. So how do we solve this? So let me go up here to finish. There's R. Okay, let me pause in case anybody... Superball, better Superball than yesterday's Superball, is dropped from a height of 20 meters. The ball rebounds to 75% of its previous height. If the ball keeps bouncing, determine the total vertical distance the ball travels. So we know that eventually this ball stops bouncing, right? And when it does, it will have gone through this infinite geometric series where we know that T1 is 20, and we know that R is 0.75, and S infinity is what we're going to calculate. So it's T1 over 1 minus R, which is 20 over 1 minus 0.75.
Don't we need to subtract 20 from it once?
Huh?
Because it's bounced, it's dropped. We need to subtract 20 from it once.
Oh, yeah, so we got a problem, right? We got the total. So if we do this, we're going to get all the downs, right? The 20. So we're going to have to double it and then subtract 20, right? Just the way we did before. So this is...
So would it be 2s infinity minus t1?
Yeah, so total distance traveled. Okay, so remember, this is what the ball is doing, right? Okay, and the 20 and all those numbers, so the 20, 15, etc., those are just the downs. There's also ups. So we need to get 2 times the sum to infinity and then subtract 20 because we never had an up 20, right? We didn't throw it up 20 in that, you know. So we could have, I mean, to go just 2 times that series could be you start at the ground, you throw it up 20 meters in the air, and then you let it bounce till it stops bouncing. And then it would just be 2 times the sum to infinity. Okay, so the total distance traveled is 140. Okay. Good. And pause. You can copy.